My name is Paul King. I'm going to be talking to you about whiskey clustering with Apache Groovy and Apache Ignite. I'm the VP of Apache Groovy and also the Groovy lead of Unity Foundation, which has been spun off from Object Computing, and also author of Groovy in Action. First up, we're going to talk a little bit about Apache Groovy. So Groovy is a multifaceted language. It supports OO style and functional. It's got a dynamic nature as well as a static nature. So you can make it be similar to Python and Ruby if you want, or you can make it very Java-like if you want. You've got both options available to you. In 2 months, we'll be celebrating 20 years since Groovy was conceived, and it's had about 2.5 billion downloads, and the rate of downloads is still increasing. So still got some popularity there. If you want to see a little bit more about Apache Groovy, there's a link you can go to, a little bit of an intro. And please come to the Apache Groovy website if you want to get more involved in the project. We're a very welcoming community and we'd love to see you there. So just a little bit about Groovy. Why should you be using Groovy with Apache Ignite? Well, if you're a Java user and you're using Java with Apache Ignite, you'll probably find you can simplify the code that you're using to access Apache Ignite. So Groovy supports most of the Java syntax, but then simplifies many different scenarios. And we'll see some examples of that shortly. And it's also very extensible, simple to learn and extensible. So Groovy was conceived because at some almost 20 years ago now, Java was evolving very, very slowly, and there was lots of features in other languages that Java didn't have, and Groovy evolved to support those features. These days, Java's evolving much more quickly. So is there still a place for Groovy? Well, yes, in fact, there's many, many areas where Groovy still adds value to Java. I'll just briefly look at two of those, but my main message over the next few slides is that if you're using Apache Ignite with Java, check out Groovy. It'll probably simplify the code that you're using with Apache Ignite. Briefly look at simpler scripting and AST transforms. Here's some Java 7 vintage code that creates a list of strings and manipulates them a little bit. That's quite a few years ago now. Coming up in Java 21, not in the current early access versions, but I believe it'll be there very soon, is a thing called JET 445, which is simpler scripting with Java. So even in Java, if you're using Java 21 and you've enabled the preview mode, you'll be able to simplify that down, use a bit of a Lambda syntax as well, and you can shrink that quite a lot from what was on the left. Groovy has an even simpler version, and that's been around since sort of Java 5 day, JK 5 days. Groovy also supports a command chain or DSL sort of syntax where you can write even simpler versions of programs. Now, for this particular bit of code, I'd probably just leave it in the form that you're currently seeing it there. But there might be times when you're using business rules or test case scenarios where this DSL syntax will become very handy. One place might be where you're using matrix manipulation. You're using a lot of formulas. You can have a simplified DSL. The code in the Groovy console there is using the exact same library calls to Apache Commons Math as the Java code on the left, but you get much simpler code to type and a much nicer output. You can see the little visual matrix there compared to the green sort of debug level output that Apache Commons Math would normally give you. If you're using notebooks, the simpler syntax can also be very handy. The other feature that I'll briefly mention, and again, the details of this aren't important, but I'm going to mention one of Groovy's features, AST transforms. It's a compile time metaprogramming technique. This is some code following the sort of effective Java guidelines for how you write an immutable Java bean person class. Details aren't important, but you can see there's lots of lines of code there. Groovy sort of says, well, most of that's boilerplate, so why not let the compiler generate that for you? And that's what it will do. Since that Java code was mainstream, Java's evolved, and if you're on Java 16 and above, you can actually simplify the boilerplate a lot as well and use a record. Groovy will support that as well. Groovy's record support is very rich in that it'll support emulated records back in earlier JDK versions, and in later JDK versions, it'll do native records and add more features, optional methods to map, to lists, and so on. So there's a lot of bells and whistles that Groovy adds to records if you want to use those. Over and above that, there's many more. I showed you add immutable as an AST transform, but there's lots of them. So I can mix in at sortable, auto externalize, index property, and instead of saving tens of lines of code, I can save hundreds of lines of code. And the background of this slide is the hundreds of lines you'd need to write in Java to simulate that Groovy code. And there's lots of those AST transforms. I won't go into them today, but if you've got some boilerplate code somewhere, Groovy might be able to simplify that for you. Okay, so the message is there is if you're using Apache Ignite with Java, consider using it with Groovy. Next topic is Apache Ignite. Hopefully through this whole conference, you'll learn lots more details about Apache Ignite. For us, we're basically using it as a distributed cache. We've got our data set. It'll be partitioned across nodes potentially, and we're going to use that capability, but we're also using the distributed machine learning algorithms. So the middle slice in the little picture on the right-hand side there, k-means, regressions, decision trees, and so on. There's some pre-processing stuff as well. They're all distributed algorithms that are part of Apache Ignite. So we're going to be using those. And if you go look in the Ignite documentation for the Groovy examples of using those, you won't see them, but you'll see the Java examples, and Groovy is so close to Java that it doesn't need any special APIs. It just uses the Java APIs, and you'll get a lot of Groovy's boilerplate reduction automatically. And there's more you could add if you wanted to, but we won't go into that today. The next topic is data science. I'm really just trying to let you know that we're going to zero in on one very small part of data science and one algorithm. There's lots to it, and probably all the topics worth their own talks, but just letting you know there's more out there. There's lots of different phases that you'd probably want to look at if you're doing data science. We're going to zero in on the sort of data modeling, data processing part of it. Groovy's got some good things in a few of the different bits, as does Apache Ignite. I won't elaborate any further on those. And just another slide that talks about a number of the different aspects you'd probably also want to consider if you're doing some data science. We're going to zero in on one particular part of it, but just be aware there's much more that we could look into. This is a slide showing a whole bunch of different algorithms. Don't be too concerned if you can't, if you don't know all the algorithms there. You can't, even if you can't read the writing. We're just going to be looking at one of the algorithms, clustering, k-means. It's right down the bottom right, and we'll briefly look at dimension reduction, which through principal component analysis. So they're the two different things that we're going to look at. But Apache Ignite has regression and a few other distributed algorithms out of that picture that you can also go and look at and play with if that's the particular area of your interest or your need. Right, let's get into the case study. We're going to be looking at whiskies, and picking your favorite whiskey is a very subjective task. Some people like particular whiskies over others. Here we're looking at 86 distilleries that make single malt Scotch whiskies, and some whiskey experts have gone and graded and created a profile for each of those whiskies, and they've graded them on 12 different categories. There's sweetness, maltiness, floral, fruity, medicinal, smoky, and so on. There's a bunch of different things they've graded them on. They've created a profile, and we want to analyze all the data that they produced. So that's what we're going to look at. And we're going to try to cluster that data. So we're trying to take whiskies that are similar to one another and put them into groups. And what that would allow you to do, if you've got a particular whiskey that's your favorite, by going and looking at another whiskey in the same cluster as your favorite, you can probably find another whiskey that you might very much like as well. Or if you're trying to widen your horizons and try something different and that you have never tried before, maybe you'd go and pick a whiskey in a cluster that's different to where your favorite whiskey might sit. Now, here's some data points. This is two-dimensional data. And what does clustering mean? We're basically grouping similar items together. So the idea is anything inside the cluster is more similar to other items in that same cluster as the ones in other clusters. And ones that are in different clusters should be a bit more different from one another. Okay, and that's what we're trying to do. Now, this is not necessarily trivial for certain data sets. If I had red and white wine, I can easily split them into two categories, and then we might have some blurriness around rosé or something. For something like our whiskey data, it's actually got 12 dimensions. It's actually going to be a lot more difficult to split the data in that way. That's why we need some computer assistance, our machine learning algorithms, that get them to do it for us. And there's some other aspects that might not be obvious. For certain kinds of data, different algorithms perform better than other algorithms. So I've got a bunch of different algorithms here. Each column is a different algorithm, and each row is a different data set. I'm just going to look at the top and bottom rows and the left and right columns. K-means, which is the one that the algorithm we're going to look at first and mostly, it tries to split data into K clusters. So if I say K equals 2, it's trying to group everything into 2 clusters. K equals 3 clusters. And for that first data set, even though they're concentric rings of data, and you might think you'd cluster them around the rings, that's not what K-means is going to do. It's going to pick some clusters, center points, and then grab all the closest data and assign them to their clusters. For that particular data set, the DB scan, which is a density-based scanning algorithm, might be better, and it would group them around the 2 concentric circles. But if we go to the last row there, it's just basically random noise. The K-means algorithm is going to split them into 2 groups, just basically halve the random noise into 2 groups based on their closest cluster. DB scan just can't find anything it can't find any lower density area, and it's unable to cluster that data. So depending on your data, you might want to go and use different algorithms, and each of the algorithms you can tweak in different ways. And we'll have a look at a few tweaks that we can do when we get to Apache Ignite, and we'll see a few others along the way. First up, though, it'd be good to know, how does this K-means algorithm work? And let's have a look at how the steps that it performs. So here we've got again, I've gone to 2 dimensions to start with. It's easier for us to visualize, but this is going to be going on in 12 dimensions once we get to our whiskey example. Here's our here's our data set, our points in a 2D grid. And we just guess 5, we're going to use 3 as our K. We're just going to guess 3 random centroids. And there are algorithms that will guess the starting points for you. There's techniques for getting good starting points. Depending on what starting points you choose, you may actually get different results. So there's some things that you'll need to think about, but we're not going into the nuances of that today. So here's our starting centroids. They're just guesses. And what we do is we assign the points to their closest centroid. So you can see all the points are blue here. I'm going to assign them and change their color to match the centroid that they've been allocated to. And so you can see that some dots turn green, some red, some purple. Now what we do is let's go and recalculate new centroids based on the points that have been selected. So they're the new centroids based on the actual dots. And what we do now is we throw away our initial guess, and we've now got a recalculated centroid to start the next step in this iteration process. And we keep iterating steps 2 and 3 until it either stabilizes, so everything gets locked down and everything's at the closest centroid, or sometimes you can get a sort of an oscillating effect. A few different points here and there will just oscillate back and forth and it won't ever stop. So you might say after 5, 10, whatever iterations, just stop anyway. And that's when the algorithm will stop. So we're going to repeat those steps. Let's do one more step. Let's assign the points to their closest. And you will what you will have noticed here is there's 2 points that are red and they've now been turned green. So some of the points here are now being allocated to the new green centroid because it moved in closer to where those dots were. And again, we now calculate the new centroid and we move again. And we just keep repeating that process till we've reached a certain number of iterations or until it stabilizes or reaches some epsilon of it only moved by a very tiny amount, therefore it's pretty stable. So that's what we're going to do when we get back to clustering. And k-means, I just want to point out k-means isn't the only algorithm we could use. There's other things that split the things into trees, which is the far right graph there. Don't worry about the details on that. The end result is in the middle chart there. There'll be, again, we're going to find a way to represent our 12 dimensions into 2 dimensions, and that'll be a topic we cover shortly. And the different colors will be the clusters that we assign to them. So the green ones are sitting out on the right of that middle graph. There's some red ones there, blue ones, and some yellow ones sort of halfway between the red and the blue. So that's the sort of thing we're going to be doing. We'll look at what's involved in that shortly. The data that we've got is the first 8 rows at least are shown in the top half of that, the top third of that slide, and the little spider charts on the left are a good way to visualize. So for each of the distilleries there, Aberfeldy, Aber4, and so on, we've gone and plotted little spider chart that shows bodies to and sweetnesses to and so on in a spider chart that gives you a bit of feeling for the strengths and weaknesses, or the strong points and weak points of the different whiskies there. So just as a conceptual idea, if you've got 2 blobs out of those 8 that look similar, they're likely to get clustered the same way, but not guaranteed, because there might be just one part of the blob that's different, and that might be enough to flip it into another cluster. We'll have a look at more spider plots as we go. Now, just a couple of we're going to whiz by very quickly some non-distributed. We haven't got to Ignite yet. Non-distributed k-means algorithms and other algorithms. But before we do that, I'm particularly interested today in checking out Glen Scotia versus Glen Grant. They're both middle of the range whiskies, sort of smooth whiskies. One of them's a little bit more malty and sweet and smoky than the other. One's a bit more fruity. So what I want to do is, for those 2 particular whiskies, see whether they get put into the same cluster or different clusters. And k-means is, because they're quite similar, depending on the random starting points, depending on the number of iterations, depending on some other things I can tweak, there's no guarantee they'll necessarily be in the same cluster or different. So it'll be interesting to see how it pans out. Okay, just stepping back, if I try to visualize those 15 dimensions and the 12 dimensions using other sorts of graphs, I can, you won't be able to see the detail in these graphs. That's not important. The thing to realize is it's almost just looks like random noise. And I urge you to go and try graphing it yourself and trying to get some sort of feel for how these things would get clustered together. And it's almost impossible. That's why we need the sort of clustering algorithms to do that for us. And here's what happens. This is using again non-distributed, so just in a single machine. I think a little tool called Weka, and I ran its k-means, and it came up with 5 clusters. I told it k equals 5. It came up with 5 clusters, and it's gone and I've printed those out, and I've printed out the little spider chart, and you can see for one of the clusters, it's got the red. It's got a red sort of square boxy looking thing sticking out on the right. That's where you'll find a whole bunch of whiskies that have got high smoky and medicinal grades in their ratings, and there might be a blue one that's ones that are winey and nutty and malty. They might be a different cluster, and it's gone and grouped all those together, and it's spat out the result that it got. And for the starting points that it picked and the number of iterations I ran for this particular algorithm, it went and put Glen Grant and Glen Scotia in the same cluster. So we'll see what happens when we get back to Ignite shortly. Did another one where I chose medoids instead of centroids. So centroids in our previous chart, it's just a random point that happens to sit in the middle of all the different whiskies, and it's just a random point in the middle there. I can go and pick the medoids if I want, and there's a little example that does that using Apache Commons math. Don't worry about the code on here. That's not important. It's just not very many lines of code to run this algorithm and to plot the graph is all that's going to kind of show you. The end result is it came out with these centroids up the top, and the last column there is the medoid. So what it went and did was picked the whiskey out of the cluster that is closest to where the centroid was, and that's like a typical stereotypical example of a whiskey, the best example of a whiskey in that cluster. And that's what your medoids is there. There's some examples. For the rest of the talk, I need to talk about one more concept: dimension reduction. And we've got 12 dimensions, and we need to somehow visualize that. And here's a little graphic that shows you how you turn 3 dimensions into 2 dimensions. We're going to be turning 12 dimensions into 2, 3, or 4 dimensions. And I won't go into the details of how that works, but there are algorithms to do that. And we want to not lose information as we reduce the dimensions. And that's all we need to know for now. If we go and run that, here is some little 2-dimensional charts of our distillery data. So there's 86 points on each of those charts there, and it's been mapped into 2 dimensions. So even though there's 12 dimensions in our data, we've gone and ran it through an algorithm that grinds it and massages it into 2 dimensions. And then what we've done is we've run k-means, and we've done it for 2, 3, 4, 5, and 6 values for the k. So we've got 2 clusters up to 6 clusters, and it's gone and assigned all the groups, and then it's used different colors to show where the different distilleries match. And I won't go into what a scree plot is, but basically it's telling me that the 3 clusters is probably the one that splits apart the clusters best. And that's all we need to know for that. I've gone and used, we haven't got to Ignite yet. I'm using Weka, and I'm using some of these are k-means, some are self-organizing maps. I've got Canopy. I've got different clustering algorithms here, and you can see they've all got very slightly different groupings in the clusterings. So again, those charts will be very small. Don't worry if you can't see the details, but you should just notice that there's different colors in the different charts. Another thing to notice is the size of the dots are very slightly different. So when I ran the PCA, the principal component analysis algorithm for this example, I said use 3 dimensions, and I used X and Y as 2 of my dimensions, and the size of the bubble is the 3rd dimension. And we can go one step further, and we can actually render a 3-dimensional chart. Again, don't worry about the code here. This is actually a nice interactive plot that it'll pop up in your browser, and you can rotate it around and visualize where all your points are in 3 dimensions, where the centroids are, which are the big blobs in the middle there. You can see the little dots and the big blobs. That's the centroid. And we could actually tell it 4 dimensions, and it'll actually change the size of the little dots as well. So you can actually get up to 4 dimensions. It's impossible. It's very difficult for humans to visualize more than 4 dimensions. 5 dimensions, you kind of need time or something as one of them. You could use color, but then we can't represent our clusters very easily. So yeah, that's the kind of thing that we want to do to visualize what's going on. And I showed a dendrogram before. This small amount of code, if you want to go and use a different way to do the clustering rather than the k-means, there's a different way here, and it gives very slightly different groupings. This is just to let you know there's more options you have available to you if you want. Right, let's get on and look at Ignite now, and how to do this in a distributed. If you've got a distributed set of nodes in a cluster, how you do a distributed clustering across those nodes. Now, one thing that might not be obvious when we looked at the k-means algorithm is there's an assumption here. So step 2 was assign points to the closest centroid. Well, we're assigning all the points to the closest centroid. So it doesn't really work if I've only got part of the points there. I won't get the accurate centroid according to what the k-means algorithm would try to do. But in fact, it does still work with a little bit of a tweak. And what we do is we partition the data, as Ignite is going to do for you, and we run the normal standard k-means across each of the nodes. And what we then do is, so after we've got our iterating steps going around, but in between each iteration, as we cycle through those steps 2 and 3, we do an aggregation and a redistribution step. And so what we do is we get the results from each of the nodes, we combine them and merge it into, we average out the centroids, if you like, and we send that back to each node. Now, what this, you might think, have we saved ourselves? Well, if we've got thousands and thousands of points, k-means in its native form, we'd have to share thousands of points across the nodes, which kind of defeats the whole purpose of doing things in a distributed fashion. Here, the only thing we share is just the center point. So it's a very small amount of data that we have to share. And it actually works out really nice to distribute this algorithm. And so then we send that data back, and that's the thing that we use for the next iteration. And so now we cycle around doing normal k-means, but with this little aggregation step as we go. So we'll look at the code for that. The codes, I've done a slight simplification. If you're using Apache Ignite, you're probably going to want to go and use its features for loading in your data from various sources. For our simple data, I'm just going to use Apache Commons CSV. It's not the part of the code that I want to highlight. We're going to select our regions of interest, so we can use Groovy's got nice syntax for selecting out. If we look at distilleries, we're going to look at, that's the green part. We're going to look from the first row to the end row, and we're going to get the first column for all of those. For the features across the top, we're going to look at row 0 from column 2 to the end, and the yellow data is from the first to the last row, from columns 2 to the end, and we're going to collect all those. We create ourselves, we do a little bit of configuration. Now here I've kind of cheated a little bit, and I've got it running on a single node. You might think, wasn't the whole point of this talk to run it in a cluster? Well, the point is that I don't need to change the code for it to work in a clustered multi-node environment. I just change the configuration. And all my code that most of it's on the next slide doesn't need to change. So I happen to be using a single one, but we could easily just go and change the config here, have multiple nodes, and everything else will just work as before. And we can go put that in, config in some XML if we want. I've got some little helper variables. One of these I'm going to come back to, which is a distance measure, Euclidean distance. It's one of the things I can tweak when I'm using k-means. And I've got a little helper which is going to take my double array and put it into vectors, which is what Apache Ignite wants. And a little thing to help me print things out. So here is now my code. I basically populate Ignite's data cache from the data that came from the CSV file that I read in. I create a k-means trainer. I give it the distance measure, which was the Euclidean distance. We'll come back to that. And tell it I want 5 clusters, and then I tell it to fit the data, and it's pulling it out of the cache, and it's doing it across distributed nodes if that's how I configured things. And then I'm just going to go and print those out and tidy up after myself. And this is what it prints out, and there are my centroids. Okay, I can go a little bit further, and I can show you some querying. Using Apache Ignite's querying, so it'll query across the distributed nodes if I had them configured that way. And I can run them the previous step calculated the model. Now I'm running the model on all the data and spitting out which cluster things got assigned to. And we can see here now that Glen Grant got assigned to cluster 1 and Glen Scotia to cluster 5. So maybe the extra maltiness or whatever else that was in one of them has been aligned with the other things that are of that nature in its clusters. So it had a slightly different result. Again, if I started with different starting points or I tweaked some of the things I could tweak, we might get different results. Let's look at one of the things I could tweak for k-means, and it was that distance measure. I mentioned it before, Euclidean distance. And if I'm going between 2 points here, 3 steps across, 4 steps up, if you remember the square root of x squared plus y squared type of thing, that's the Euclidean distance between 2 points. And I can use that as my distance measure, or I can swap to Manhattan, which Manhattan is walking through the streets of Manhattan. I can't walk through the building, so I have to walk horizontally and then vertically in the little picture there. And that's going to give me a distance measure of 7 for those same 2 points. And so if I've got lots of little differences, that sort of extenuates those. For us, Euclidean is probably better. If I go flip back and forth between those, when I'm using the Manhattan measure, my clusters seem to be closer in and more similar to one another, whereas the Euclideans tease them apart a bit more. So I think Euclidean is the go for us. Very slightly different clustering groups, but it's not that important for us. We can go and tweak things to go and use a different, rather than k-means, Ignite has some other cluster, well, at least one more clustering algorithm built into it, and it's a Gaussian measure algorithm. And it's, rather than any single point, trying to work out which is the closest point to the cluster and sort of having a very black and white ruling on where things go, it says everything's on a normal curve. And so if I've got a point that's sort of halfway between, it might have a 30% chance to belong here and a 40% chance to belong to there. And it kind of lets you have softer sort of clusters. Anyway, we run that, and it's actually got it's one of the algorithms that chooses its own number of clusters. We give it a hint. We say no more than 5, and it goes and says, it works out the clusters based on its calculations for where it thinks it's done a good split. And it came up with 2 clusters, and the red and blue colors there are the 2 clusters it came up with. So you've got more options even with Ignite, and we can tweak the different algorithms. So there's various things. And as I mentioned before, Ignite has things outside clustering that you might want to go and look at if you're in other spaces in machine learning. Okay. That's all I wanted to cover. There's some details there to get in touch with me. If you want these slides, you'll get links to those. There's all of the code, including both the Ignite ones and the non-Ignite examples, are all in that repo there. Okay, time for questions.
Right, Paul. Well, thank you for that. And welcome back to the stage. Let's run through some questions for you. You've told us a bit about what, to me, as I said, is a fascinating topic, using AI and Apache Groovy, Apache Ignite all together. Do you have any other examples of using Apache Groovy with Apache Ignite?
Yeah, so the repo, that there was a link there in the slides, and when this stuff gets tweeted around after the talk or whatever, you'll see it links to both the code and the slides. In the full repo, there is an example of linear regression. So it's using Apache Ignite with Groovy to predict house prices. And so that's an interesting example as well. And that's using a different part of Apache Ignite. There's a distributed linear regression algorithm, least squared type thing. And again, it's another one of those algorithms that when you, for least squared, you're adding up all the errors from a line to get to sort of find the line of best fit. And you think it's one of those algorithms, oh, well, I need to know where all the points are if I'm going to work out where the line is between. So you think it's, oh, this is one that you can't distribute, but there's been people have done some smart tweaks to make algorithms like that distributed. And yeah, so that's another example there.
Okay, here's another question. Is there a feature from your perspective in this domain that's not in Apache Ignite that you'd like to see?
Yeah, so Apache Spark has a distributed version of that principal component analysis. That was the thing that turned the 12 dimensions into 2 or 3 or 4, depending on whether I'm wanting to use bubble sizes and colors and things. But Apache Ignite doesn't have the equivalent for that, and I'd be interested in if that was available. It's an algorithm that tends to get less interest because it's not really giving you anything extra for your model, but when you want to visualize it, it's quite important. So it's not as critical, I guess, but it certainly would be something that I think is it's kind of nice once I've gone and got my model to visualize what's going on. It's gone and clustered these things, or it's gone and best fitted this line or whatever, and you're trying to visualize things. Yeah, principal component analysis would be something I'd like to see. So I don't know how easy that is, but Apache Spark has gone and done it, and there's certainly papers out there that talk about good and bad ways to do that sort of thing. So yeah. Oh well, yeah, I've contributed to. There's been a clone of Apache Commons Math that named after a Greek mathematician or something, but and I've contributed a PCA to that, but I haven't looked at how to distribute it yet. But I might do that. Yes.
Another question on k-means model. So could the train k-means model be used together with the Ignite affinity function to get speed up in recommendations? You were looking you were looking at a single.
It might be a good thing for speeding things up, but it's more important. What I didn't go into the details of, the algorithm there was calculating centroids on all your clusters and then aggregating them. Now, if your data has been partitioned to have stuff that's very disjoint on all your different clusters, you're not going to get good representative centroids being calculated. So imagine those points, if I push them all into 3 sections and they were actually the clusters with my data, each time I ran that, each one would be giving very distinct centroids, and then you try to aggregate them and it wouldn't work too well. So what you want is a good representation of the breadth of your data across all of your partitions, and so you'd want an affinity function that honored that aspect.
Great. Okay. We have a question from Chris Goodall, and the question is, what other solutions are out there that allow you to distribute this type of AI processing, and why is Ignite so appropriate?
I like Ignite because it offers a very simplified way of doing this. So that there's Apache Spark has similar algorithms. It's a little bit more complex to set up and a little bit more complex to work out what's going on at times. There's a few other alternatives that let you do this sort of thing as well. I roll my own with a Groovy library called Jeepers, which has got sort of data flow and parallel arrays and a bunch of other stuff. And when I showed those little graphs of the algorithms, that algorithm is built into Ignite and built into a Spark, so you don't need to do anything. But you can just do that algorithm yourself if you've got any sort of just something that supports actors or any distributed got Vertex. You can build your own distributed things on there. I've used Apache Beam and Apache Wayang and other things as well. But again, for those two, they don't have the distributed k-means, but they give you the clustering environment. And you have to do the algorithm yourself when you're using those. So really the two best ones for this particular problem would be Spark or Ignite. And I think Ignite gives you a simpler environment for doing this particular problem.
Great. Okay. Well, I think that's all we've got time for today, Paul. So
Okay, brilliant.
thank you very much for joining us.
Thanks very much for having me. And yep, my contact details are spread everywhere. If people have got additional questions, they can get in touch with me. I'm more than happy to answer further questions.